Hi everyone, my name is Dima and you're on the Science Rock channel. We're constantly surrounded by a huge amount of electronics. These little boards with electronic brains are practically everywhere. Some of them are even connected to the internet and spy on us. But how are they made? In this video, we'll design and build a simple electronic device from scratch. As always, all the source files and materials for building it yourself are in the description. To demonstrate different technologies in a single device, let's create a wireless toy. Let it be a small steering wheel that you can connect to your phone or computer via Bluetooth and control, for example, cars and games by tilting it. What will this device consist of? The device needs to be autonomous, so it should have a battery. And since there's a battery, it needs to be charged, so let's add the necessary charging components and a USB-C port to plug it in, a charging cable. The steering wheel is wireless, so it needs a Bluetooth antenna. Since we need to determine the tilt angle of this steering wheel, we'll need an accelerometer and a gyroscope, just like the ones found in all mobile phones. It will also be useful to add a couple of buttons to control the throttle and brake, and a couple of LEDs to indicate when the device is on and when Bluetooth is connected. And now the most important part, the brains. They will read the sensor data, process it, and send data packets to the outside world via the Bluetooth antenna. This role will be performed by a microcontroller. I also want the device to be in a keychain form factor and as small as possible. That's why we'll try to minimize both the number and the size of the components. All of this will be implemented as a printed circuit board with components soldered onto it and placed inside a plastic case. Designing the board is our next step. It starts with creating a schematic diagram. This is a diagram that shows in detail the symbols of specific components and all the electrical connections between them. There are various programs for creating schematic diagrams. I use Altium Designer, but there are plenty of alternatives. Let's get started. We'll begin by choosing the main microcontroller device. This is a type of microchip that includes a processing core, memory, peripherals, and many pins through which it can interact with other devices. Essentially, it's almost a fully functional programmable computer, just smaller and consuming only about half a watt of power. There are a huge number of different models, from simple 8-bit devices made up of a million transistors to 3 GHz 64-bit monsters with external memory and dozens of billions of transistors, capable of running a full-fledged operating system and performing trillions of floating-point operations per second. These are found in modern mobile phones, watches, and single-board computers. If you had shown such power to developers from the era of the first personal computers, you would have been burned at the stake. However, many modern programmers still manage to write code that lags even on such insane hardware. But for our task, there are no performance requirements at all, so even the weakest piece of silicon will do. I'll choose the NRF52832 model from Nordic Conductors. It's much more functional than necessary, but it's great because it supports Bluetooth Low Energy, which is suitable for our project. And also because I already have one. It was left over from one of my old projects. Here it is. So, how does a microcontroller actually work? If you take off its cover and look under a microscope, you'll see a pattern made up of many blocks, each consisting of tens of millions of microscopic transistors. There is an area of permanent flash memory where we will later upload our firmware, a processing core that performs mathematical and logical operations, RAM, and various peripherals for interacting with external devices. Timers, and areas for clocking and power supply. All the magic begins with power and clocking. As soon as we supply power to the chip, its clock generator starts up. It simply generates periodic rectangular voltage pulses, which are needed for clocking and synchronizing all the blocks. But this built-in generator is not perfect. The frequency of the pulses can fluctuate slightly due to the influence of temperature or other conditions. Such instability doesn't suit us, because extremely high clock accuracy is critically important for Bluetooth operation. That's why we need to install a Quartz resonator. Essentially, it's just a piece of quartz of a specific size and shape with 2 pins connected to its ends. Quartz is a piezoelectric material, so when we apply voltage to the pins, it deforms slightly, which generates a response voltage. The shape of the quartz. At the factory, it is specially made so that the resonant frequency of its mechanical oscillations is predetermined. In our case, it's 32 MHz, that is 32 million oscillations per second. If you apply an electrical pulse to it, it will oscillate exactly at its resonant frequency, just like if you struck a tuning fork. And this is what it looks like. Damn. The controller has special pins to which you can connect such a resonator. and then it becomes part of the clock generator circuit and will maintain its frequency with very high precision, regardless of temperature and other conditions. The resulting pulses are distributed to all blocks of the microchip and synchronize their operation. With each pulse, the controller core reads the next instruction from memory and executes it. This could be, for example, adding two numbers and writing the result to RAM, or measuring the voltage on one of the chip's pins, or sending a signal to an external device. All these instructions are stored in memory as binary code, or in common terms, firmware. We will write the firmware in C++ and upload it to the controller's memory using a programmer. To interact with the outside world, the controller can send binary signals to its pins in the form of sequences of high and low voltage. Or conversely, it can read the voltage level. For example, if we want to control an LED, we connect it to one of the pins and apply high voltage to that pin. Then the LED will light up. And if we want to respond to a button press, we connect the button and read the state of the pin. If the button is pressed, the voltage on it will be low, and if not, it will be high. And to transfer data between different digital devices, we can generate or read complex sequences of high and low levels of voltage. To place a component on a schematic, you need to create its schematic symbol. This controller has 48 pins, and all of them need to be drawn. To understand the purpose of each pin, we go to the Nordic Semiconductor website and open the datasheet for this specific chip. It contains 600 pages, but of course we won't be reading all of them. Let's open the page with the pin assignments right away. Some pins here are responsible for power, some for clocking, some for firmware uploading, and others for various service functions. But most of them are general purpose pins, to which we will connect other components. There's also a ready-made schematic diagram with labeled pins, which for clarity can simply be replicated in Altium. Open the component editor, create our chip, and draw its image with the pins. For simplicity, we'll draw it exactly as in the documentation and label each pin according to its designation. Done. Now we can transfer this to our schematic diagram. Now it needs to be powered. To do this, let's add a battery to the schematic. The battery has only two pins, plus and minus. Let's represent it as such an element. A fully charged battery provides a voltage of 4.2 V, but the microcontroller requires exactly 3.3 V for power. If you supply more, it will simply burn out. That's why we need to somehow lower the voltage from the battery. The simplest solution is to use special voltage regulator chips. You can supply any voltage above the set value to their input, and at the output you get a stable set voltage, in our case 3.3 V. The principle of its operation is that the higher the input voltage, the greater the resistance it adds to the circuit. This way the voltage at the output drops to the desired level. At the same time, it simply dissipates part of the power as heat. We install such a microchip and connect it to the battery. Now from this microchip we can already power our microcontroller. Other components will also be powered from it. Before we go any further, we can immediately connect an LED to indicate that the device is working. If we connect it like this, then when power is supplied, current will flow through the LED from the anode to the cathode, and it will light up. And one more LED. We'll connect it to a microcontroller pin so that it lights up according to a condition we specify in the firmware. Let's make it blue. Let's move on to the tilt sensor, accelerometer. An accelerometer is an acceleration sensor. In simple terms, it looks like this. Inside, there is a microscopic weight on springs. It can shift when the sensor is tilted due to gravity or during acceleration. The built-in electronic circuit applies a high-frequency voltage between the weight and the wall and measures the current that flows as a result of this voltage. And the amount of current depends on the distance between the weight and the wall. This way, the system can determine how much the weight has shifted. And from the displacement, you can also calculate the tilt. They are manufactured as microscopic chips. This is what it looks like under a microscope. Two microscopic combs made of conductor form a capacitor, whose capacitance increases as one enters into the other, which is measured by a special high-frequency sensor. But all of this stops working if we shake the device from side to side. The weight shifts, but there is no tilt. So, one accelerometer won't be enough for us. But there are other types of sensors as well, gyroscopes. A gyroscope measures its angular velocity, that is, how many degrees per second it is rotating. It is currently rotating. Previously, mechanical setups with large heavy flywheels spinning at enormous speeds were used for this purpose. But in modern compact electronics, there are microelectromechanical gyroscopes about the size of 1 cubic millimeter. Their operating principle is more interesting. Inside, there is a microscopic ring that vibrates under the influence of a piezo element and an electrical generator circuit. Linear accelerations do not affect it in any way. But when we start to rotate it, the axis of oscillation turns by an amount proportional to the angular velocity due to the Coriolis force. This rotation is detected by the built-in electronics. But the gyroscope also doesn't give us the information we need, because we need the tilt angle, not the rate at which it changes. However, we can use it to solve the accelerometer's problem. Now, if we shake it, the accelerometer will react, but the gyroscope will show 0. This way, we can distinguish shaking from tilting and get clean data about the device's tilt angle. So we will need both an accelerometer and a gyroscope. Often, sensor manufacturers produce both in a single package. Here's an example of such a sensor from Bosch. It contains 3 accelerometers and 3 gyroscopes arranged in 3 perpendicular planes, which allows tracking rotation along all 3 axes at once. Let's add it to our circuit and connect the power right away. We also want to have throttle and brake buttons on the handlebar. Let's take the simplest small buttons, which are sold in any electronics store. They need to be connected to the microcontroller so that our firmware can detect their state and use it in its logic. To do this, you can use any convenient pin on the controller and connect it to the power supply through a resistor. And if the firmware reads the state of this pin, it will get a high signal. Now let's connect the button between this pin and the ground. When the button is pressed, it will directly connect the controller's pin to ground, and then the firmware will see a 0. This way, we can detect when the button is pressed. Now we need to connect the accelerometer and gyroscope to the controller so it can receive data from them. How do microchips exchange information with each other in general? There are various digital data transfer protocols for this purpose. One of these protocols is called I2C. It uses 2 pins. One of them transmits a digital code with the device identifier and useful data, while the other carries synchronization pulses. On the receiving side, the microchip reads the voltage level on the data line, with each pulse on the synchronization line. At the same time, information can be transmitted in both directions. By the way, you can connect more than 2 devices to the I2C interface. The main thing is that each has a different identifier, so the main controller can pull them one by one. Our controller and sensors support this protocol, and they have special pins for it. So it's no trouble at all to connect them to each other. To avoid running wires, you can simply use these jumpers to connect the pins. Let's get back to the battery. It needs to be charged somehow. Charging will be done via USB, so let's add a connector to the circuit. But you can't connect it directly to the battery because the USB interface has a higher voltage. It's 5 volts, while the battery needs 4.2 volts for charging, and with current limitations as well. Fortunately, there are special chips designed for this kind of conversion. A simple one will do for us, so we'll add one of those to the circuit. And an LED, so that it lights up when charging is in progress. Let's move on to the last of the most important components of the circuit, the wireless data transmission system via Bluetooth. As I mentioned before, our controller supports Bluetooth. This means that inside it, there is almost everything needed to generate a high-frequency signal, which will be transmitted through the air via an antenna. We just need to add this antenna and a couple of matching components. And finally, let's add a Quartz resonator, a power-off circuit to save battery life. And various auxiliary components needed to smooth out ripples, manage power, and a connector for flashing the firmware via a programmer. So the schematic diagram is ready. Now we know exactly which components will be on the board and how they will be connected. All that's left is to design the physical implementation of the board itself. A printed circuit board is a flat piece of dielectric material with pads for soldering components and copper traces that connect these pads to each other. The traces are usually located not only on both sides of the board, but also inside, in layers, with many vias that allow a conductor to dive from one layer to another. Sometimes, when there are a lot of connections, the number of layers can reach dozens. But in our case, a simple 2-layer board is enough. The first thing we need to do is draw the footprints for soldering each component. We take the documentation and precisely redraw the pads for each component, making sure to follow all the dimensions. Additionally, you can link a 3D model of the component so you can later view the board in 3D. The footprints for other components are drawn in the same way, but the antenna deserves special attention. Purchased antennas are often used in portable devices, like these or these, but we'll take a simpler approach. All we need to do is just draw this antenna. In fact, an antenna is simply a conductor of a certain shape and size, which depends on the frequency of the emitted radio wave. And we can make such a conductor as a trace on the printed circuit board. We won't even have to buy or solder anything. After drawing all the footprints, we move on to creating the actual board. We click the button, and Altium takes all the footprints we've drawn and transfers them onto the board layout. Now our task is to arrange them correctly and connect them with traces. Altium uses the schematic diagram we created earlier to suggest which pins need to be connected to each other with traces. First, let's draw an approximate outline of the board. It can be any shape, since at the factory it will be cut out by an automatic milling machine anyway. I chose a rectangle measuring 20 by 30 mm, which matches the size of a typical compact battery. Now let's roughly place the large components: buttons, USB connector, antenna controller, programming connector, and so on. I'll place the taller components on the back side of the board and the shorter ones on the front, because the flat battery will later rest on them. Well, now we can place all the remaining components and start creating the traces to connect them. The traces have to be drawn manually. In general, there are auto routers for this, but so far they work very poorly. When routing, you need to take a lot of nuances into account. The values and frequencies of the currents, parasitic capacitance, inductance, electromagnetic wave emission, and absorption, all of which are especially important for high-frequency devices. You should try to arrange the components in such a way as to minimize the number of trace crossings. And where crossings are unavoidable, we place these vias, holes to the back layer. And then we continue the trace on the other side of the board. Finally, the routing is done. Now let's turn on 3D visualization mode and see what our board will look like. Look how beautiful it is. This 3D model will come in handy for designing the case and for 3D printing. The board is ready, so we can send it to the factory for manufacturing. It costs about $30 for 20 solar pieces. There's no point in making fewer, because it will still cost $30. Well, while it's being manufactured, we can design a nice case. I asked a neural network to generate a few case sketches. It's not exactly what I wanted, but I think it's enough to get started. For 3D modeling, I use SolidWorks. Let's start with the top cover. We'll draw the outline and extrude it to make this kind of shell. Let's smooth out the corners and cut out a cavity for the electronics. Now let's make holes for the buttons. And for the LEDs. Let's put all of this together with the board model into a single assembly, and see how it all fits together. Looks fine. We can start printing. You can't just feed these models directly to a 3D printer. First, you need to slice them into layers and turn them into specific instructions for controlling the printer's motors and heater. This is done very simply. We load the models into a special program called a slicer. We set a billion different settings and parameters and press the slice button. As a result, we get a visualization of the plastic layers and a G-code file, which can be fed to the printer. We start the print, It turned out smaller than I expected, but it came out pretty well. Now we just have to wait for the boards to arrive. Finally, the long-awaited package has arrived. Let's see what's inside. We can start soldering the components. Usually people use stencils, special placement machines, and reflow ovens for this, but in our case that would be a bit too much. So we'll just do everything by hand. First we apply the solder paste. Then we use tweezers to place the components. And heat it up with a hot air gun to 300 degrees. Watch how beautifully the paste melts, and the components, thanks to surface tension, settle perfectly into place. The board is ready. The first thing you need to do with a new board is make an LED blink. To do this, you need to write code and upload the firmware to the controller's memory. We open the editor, I'm using Visual Studio Code for this, and write the LED blinking algorithm. Our LED is connected to pin 13 of the controller, so we need to initialize this pin as a digital output. Then we start an infinite loop in which we apply a high voltage to this pin, wait for 200 milliseconds, and then apply a low voltage. And again, we wait for 200 milliseconds. That's the entire code. The controller will change the voltage level on pin 13 every 200 milliseconds. We connect the battery, compile the code, and upload the firmware to the controller's memory using the programmer. There we go, the LED started blinking. This means everything is working as it should. Now we can write a full-fledged firmware. I won't go into details, I'll just describe what blocks the code consists of. Here we have the setup of pins and peripherals, Bluetooth protocol initialization, creation of high-D descriptors so the device is recognized by everyone as a gamepad, configuration of inertial sensors and buttons, and the code for polling sensors and sending data to the host. Let's check it. The phone detects Science Rock. Device. Connecting. And launch an app for testing gamepads. Everything works. Now we can put the board into the case and launch some game. Everything works, but I want something more tangible. I happen to have a lot of various electronic junk lying around, from which I can assemble a little car. I programmed it as a host to which a wireless gamepad can be connected. It can move in any direction, and I assigned rotation to the buttons. If you enjoyed the video, subscribe and I'll share more interesting things. Bye everyone!